Welcome to the course Excelling with Mathematical Modeling. Today we will be talking about a tumor model with immunotherapy. Now, what is this immunotherapy? So, it is a kind of cancer treatment, and generally a component is made, or our immune system, that generally tackle this cancer and try to destroy the cancer cells. So, inside our body we have these T cells, which is our second line of defense. So, whenever a virus or any cancer is formed inside our body, see, the body sends this T cells to destroy and kill the foreign objects that gets inside our body. So, there are many kind of immunotherapies. First is, say, the monoclonal antibodies, then we have oncolytic virus therapy, we have cancer vaccines and T cell therapy. There are many more, I just named 4 of them. In this model, we will be using this T cell therapy as our immunotherapy. So, why we go for this immunotherapy? Obviously, there are chemotherapy and other treatments. So, sometimes it boosts this immune system, and without some side effects, just as the chemotherapy has, it generally allows or stops the growth of these tumor cells. So, what are these T cells? So, they are a group of white blood cells known as lymphocytes, and they play a central role in cell mediated immunity. The one which directly kills the cancer cells are called cytotoxic T lymphocyte or cytotoxic T cells. So, they generally find these cancer cells and directly kill them. There are another kind of immune cells, it is called T helper cells or TH cells. So, some sort of secrete some kind of protein that boosts this cytotoxic T cells, or in short TC cells, and once they activate those, they find the cancer cells and kills them. So, a little bit of biological background is needed while you form this tumor model. So, basically you have a T cell, it is classified into 2 parts, one is this TC cell, one is this TH cell. TC cell or cytotoxic T lymphocyte, they directly kills the tumor cells or cancer cells, whereas TH cells, they secrete some kind of protein that actually boosts this cytotoxic T cells to kill more tumor cells. So, the mechanism goes like this, that you have this cytotoxic T lymphocyte or TC cells, they are the killer cells of the immune system. They release some kind of protein which is called perforin and some enzymes which is called granzymes. So, what is the work of perforin? The perforin that creates a pore in the cell, and through that pore these granzymes they pass and activate certain enzymes that leads to apoptosis, which is a programmed cell suicide program. And how it happens? So, what you see is a healthy cell, and some sort of chain reaction will take place, and this BCL2 protein will be inhibited. So, the idea is that there happens some sort of chain reaction which will destroy the nucleus of this cell. So, you see that this is the nucleus, and this is called cytoskeleton, which will be destroyed, and this nucleus is going to split up into smaller nuclei, that means they will be degraded, and the cell will be split up into smaller cells, and they will be eaten up by the neighboring cells, which are known as phagocytic cells. So, this is how the cells get destroyed. Now, let us look into our model. So, this is the tumor cell, this is the TC cell, that is cytotoxic T lymphocyte, which we call as the hunting cells, and this is the resting cells, which is the TH cell. This is the growth of the tumor cell, and this is where the cytotoxic T lymphocyte, that is TC cells, they kill the tumor cells. Now, this is the TC cells, this is the natural death of the TC cells, and this is where the tumor is harming the TC cells. So, when there is an interaction between the tumor and the cytotoxic T lymphocytes, so either the tumor cell kills the immune cells or the immune cells kills the tumor cells. So, that is why both the killing part will be here. Now, this is the part which I will explain at the end. This is the growth of the resting cell, and this is the part where your resting cell is being boosted up and it is boosting the TC cells, so that its number is increased, which in turn help the tumor cells to get killed. We now look into the model with the usual notations with a little modification. So, here we take M to be the tumor cells, N to be the hunting cells, whose job is to kill the tumors, and Z to be the resting cells. So, the first equation, we see that this is the rate of change of tumor, that is how the tumor increases. So, there is a constant input which is Q, and then it follows a logistic growth where R is the intrinsic growth rate of the tumor and K1 is the carrying capacity. And here there is an interaction between the tumor and the hunting cells, and the hunting cells is killing the tumor at a rate alpha 1. In the second equation, this is the rate of change of the hunting cells, and when they come in contact with the resting cells, so they are converted to this hunting cells, and which in turn helps in killing the tumor cells. So, there is an increase, and the resting cell is the source for this hunting cells. This D1 is the rate which is at which there is a natural decay of this hunting cells. Now, the resting cells also follows a logistic growth. Their rate of growth is S, which is the intrinsic growth rate, and K2 is the carrying capacity. And here this beta is the rate at which your hunting cell, your resting cell is converted to the hunting cell, and hence it has gone here. And D2 is the natural death of this resting cells. So, this explains the model of the tumor and the immune system. To find the equilibrium solution, we have to put Q plus R M1 minus M by K1 minus alpha 1 Mn equal to 0, beta n z minus d1 n equal to 0, and Sz 1 minus z by K1 minus beta nz minus d2z equal to 0. Quickly let us check this one between 3, yes. So, you solve this and you get the corresponding equilibrium points. In this case, we will get 3 equilibrium points. The first one is E1, which will be K1 by 2, 1 plus square root of 1 plus 4Q by RK1, comma 0, 0. Yes, there is one thing, there is a constant input of Q number of tumor cells in this model. So, a Q will be here. The second equilibrium point is E2, which is K1 by 2, 1 plus square root of 1 plus 4Q by RK1, comma 0, comma K2 S minus D2 by S. Now, since these are the cells, they cannot be negative. So, this must be greater than 0. So, S must be greater than D2. This is for the existence of E2, will imply that S must be greater than D2. And our final equilibrium point is E3, which is some m star, then S by beta 1 minus D1 by beta K2 minus D2 by beta and D1 by beta. Again, for the existence, this part must be greater than 0, and this m star can be obtained from the equation R by K1 m star square plus alpha S by beta 1 minus D1 by beta K2 minus alpha D2 by beta minus R times m star minus Q equal to 0. So, this value of this m star can be obtained from this equation, and these two are other two values. So, once you get the equilibrium point, you can obviously solve this m star by using the quadratic equation formula, that is minus b plus minus root of b square minus 4ac divided by 2a. So, next, once you get the equilibrium points, we go for the stability analysis. So, Jacobian matrix, say we call it V1, will be given by minus R times root of 1 plus 4Q by RK1 minus alpha K1 by 2, 1 plus square root of 1 plus 4Q by RK1, 0, 0, minus D1, 0, 0, 0, S minus D2. This is for the equilibrium point E1, which is given by K1 by 2, 1 plus square root of 1 plus 4Q by RK1, comma 0, 0. If you find the eigenvalue of this particular Jacobian matrix, you will get lambda 1 equal to minus R times root of 1 plus 4Q by RK1, which is less than 0. Lambda 2 is minus D1, and lambda 3 is equal to S minus D2. Now, for this E1 to be stable, the first eigenvalue is less than 0, the second eigenvalue is less than 0, and third will be less than 0 provided S is less than D2. So, if S is less than D2, then your E1, this equilibrium point, will be stable. Let us go to the second equilibrium point E2, which is K1 by 2, 1 plus square root of 1 plus 4Q by RK1, 0, and K2 1 minus D2 by S. The corresponding Jacobian matrix will be given by V2. So, when I say Jacobian matrix, it means that you will take this as some f1, this as some f2 and this as some f3, these expressions, and then find out the Jacobian matrix as del f1 del m, del f1 del n, del f1 del z, and similarly for the other two functions at the equilibrium point m star, n star and z star. So, your V2 will be given by minus r square root of 1 plus 4q divided by r k1 minus alpha k1 by 2 1 plus root of 1 plus 4q by r k1 0. This is 0. This is beta k2 by s, s minus d2 minus d1 0. This is 0 minus beta k2 by s, s minus d2 and minus of s minus d2. If you find the eigenvalues, they will be lambda 1 equal to minus r times root of 1 plus 4q by r k1, lambda 2 equal to beta k2 by s, s minus d2 minus d1, and lambda 3 is minus of s minus d2. Now, if you notice, for the existence of this E2, we have already mentioned that this is already positive, this is 0, this has to be positive, which will mean 1 minus d2 by s has to be greater than 0 and s minus d2 has to be greater than 0. So, this eigenvalue is always negative, this eigenvalue is always negative because of this, and we can simplify this as k2 by s into s minus d2 multiplied by beta minus s d1 divided by k2 s minus d2. So, if this particular equilibrium point E2 has to be stable, then we must have this is less than 0. So, this is already greater than 0. So, for the equilibrium point E2 to be stable, beta must be less than s d1 by k2 s minus d2. So, if this condition is satisfied, then we get your equilibrium point E2 to be stable. And finally, the equilibrium point E3, which is of the form m star s by beta 1 minus d1 by beta k2 minus d2 by beta and d1 by beta. The Jacobian matrix V3 will be given by minus alpha m star, this is 0 0 0 s 1 minus d1 by beta k2 minus d2 0 minus d1 minus s d1 by beta k2. This term is a bit big one, but here you get a negative quantity, you get something inside this square root minus alpha m star. This part you can easily calculate, but the point is that this part is negative. If you calculate the eigenvalues, you will see that one of the eigenvalue is coming to be minus square root of a positive quantity, and hence this will be less than 0, and your other two will be solved from the equation of m star. So, your lambda 2 and lambda 3 will be of the form minus p plus minus root of p square minus 4m divided by 2, where your p is s d1 by beta k2 and this part will be positive. So, if you see that both your lambda 2 and lambda 3 have a negative real part and this is also less than 0, and so your equilibrium point E3 is also stable. So, in this particular model you have seen that we have 3 equilibrium points and we have separate conditions for each of them such that those equilibrium points are stable. Let us now look into the numerical solution of this particular model using Microsoft Excel. So, we already have the model here. These are the parameter values. I have already calculated these values of m, z and n. So, let us just plot these values. So, first let me plot this . So, first we will plot two of the graphs and then the third one, and I will tell you why. So, this graph along with the tumor graph and the resting cell. So, if we plot this, go to insert, go to chart and this one. So, the chart title is Tumor Immune System. Go to this data, chart design, select data, then series 1, edit. So, this is tumor cells and this is resting cells. Okay. And next we get the time and the hunting cells. The reason we are doing the hunting cell separately is that you will see that the growth of the hunting cell is quite large, and if we put them in the same graph, the dynamics of the other two graphs is lost. So, that is the reason why we are choosing the hunting cell separately. So, you go to insert, go to this. So, as you can see, tumor immune system. Say I need a legend. Go to data, series 1, edit and hunting cells. Okay. Let me now explain this in the context of the model. So, as you can see that here the tumor cell is coming down there is a small change here with our hunting cells, resting cells, whereas the hunting cells are growing up. This kind of makes sense because this is an interaction between the tumor and the immune system. So, the immune system succeeded in bringing down the number of tumor cells to a minimum with the support of this resting cells, and as the tumor is getting killed, your hunting cells are also increase in numbers. So, this model is kind of where your immune system is able to eradicate the tumor cells, and that happens in very early stages of cancer or tumor. So, summing up, we have taken a model showing the interaction between the tumor and the immune system. We have done the find the equilibrium points, done the stability analysis, and in the numerically we have shown that with immunotherapy the tumor cell goes down. Now, in my next lecture we will be talking about the vegetation model in a desert, where we will be seeing the interaction between the water and the vegetation, and we will see the dynamics between them. Till then, bye bye.